Normally, video projectors are used for presenting images onto white canvases. If instead an image is projected onto a colored surface, the projected colors are modulated by the pigments of the underlying surface. Using a projector camera system in combination with structured light techniques, information about the surface can be acquired. By applying a pixel-precise mapping between both devices, this radiometric information can be used to calculate a compensation image with modulated intensities and colors. When projecting this image instead of the original one, the underlying surface is neutralized from the position of the camera. Non-optimized surfaces absorb more light, which leads to a reduced brightness in the projection. The diagram shows the reflectance properties of the surface with full projector illumination and without any projector illumination. Only images in which every color value lies in between both surface planes can be projected without visible errors. The area between the red planes represents the maximum range in which compensation is possible, but depending upon the input image, clipping may occur. The area between the green planes represents the conservative range, where every input image can be compensated without clipping. In this radiometrically compensated projection, the image content cannot be displayed correctly in some very bright parts due to the limited dynamic range of the projector. These errors can be neutralized manually by adjusting the brightness of the input image until visible clipping no longer occurs. However, if animated or interactive content with varying brightness and contrast values is presented, it is not possible to apply manual adjustment. In this case, an optimized automatic adjustment of the image intensities leads to a better image quality. Therefore, we apply a real-time analysis of the input image, which is used to adjust the intensities of the input image globally as well as locally to avoid the clipping errors while preserving a high brightness and contrast in the projection at the same time. The average image luminance is calculated out of the luminance channel. Out of the frequency channel, the amount of high frequencies is calculated. By computing the threshold map, the maximum non-perceivable luminance variation at each image pixel is acquired. Using the results of the image analysis described, our algorithm adjusts the intensity globally as well as locally to neutralize the underlying surface while preserving a high overall brightness in the projection. The whole analysis as well as the additional intensity adjustment is implemented via fragment shaders on the GPU. In combination with multi-pass processing realized with frame buffer objects, the complete algorithm runs in real time. In the following, we show several compensated video examples projected onto different surfaces. These videos are projected onto a wooden panel. While a traditional compensation algorithm was used on the left, the results of our adaptive algorithm can be seen on the right. In this example, the content is projected onto striped wallpaper. These video scenes are projected with radiometric compensation onto a natural stone wall. Particularly when the presented content varies greatly in brightness and contrast, the adaptive content adjustment generates an improved image quality. We used a Pentium 4 processor with 3 GHz together with an NVIDIA GeForce 7900 GTX for performance evaluations. With this setup, content in PAL and XGA resolution can be compensated in real time. This diagram shows the results of 4 video scenes presented in the test study, which was carried out by 32 participants. All projections were displayed with a traditional radiometric compensation algorithm and our adaptive solution. In all 4 tests, a clear preference of our algorithm can be seen, which shows that a perceived improvement in image quality can be achieved. We believe that these techniques are essential for upcoming mobile projection devices such as pocket projectors and devices used in cell phones, PDAs, and digital cameras.